Let me welcome you to this lecture. We have now discussed about three different classes of compounds of boron. That is, we have discussed about the metal borides. Then we have also discussed about the chemistry of hydrides of boron. And finally, we discussed about the chemistry of boron oxygen compounds. So during this lecture, we will discuss about the chemistry of boron halogen compounds. As such, there are numerous boron halogen compounds have been already reported. That is, numerous boron halogen binary species. And the most prominent and the most well-known among these binary boron halogen compounds is the boron trihalide. You may already know that we have compounds like BF3, BCl3, BBr3, and Bi3. These are the four trihalides of boron, and these compounds can be considered to be the first member of the homologous series, that is Bn Xn plus 2. So in case of the trihalides, the N is equal to 1 and we have 3 halogen atoms are attached to the boron centers. We'll discuss about the chemistry of these trihalides in more detail. Then we also have the second member of this particular homologous series, that is, we have compounds of this formula, so that is the dimer B2X4. These sort of compounds are also well known for all the halogens. So that is, we have B2F4, we have B2Cl4, B2BBr4, as well as B2I4. All these four are B2X4 type of compound have been already reported, and their structures are also known. Now, the boron fluorides, in case of boron fluorides, actually the higher catenated species are also known apart from these dimers. So we have compounds like B3, F5, B8, F12. These sort of higher catenated binary boron halides are known only for the fluorides, only for the fluorine, but not for the other halogen atoms. So these are some very interesting type of binary boron halogen compounds. Apart from these, another very interesting class of boron halogen compounds are also well known. That is, these compounds, that is Bn Xn type of compounds, or they have this sort of formula. They have closed polyhedral skeletal structures like the boranes or the closoboranes. They have closed structures, and examples of when X is equal to Cl. So for the chlorine, we have N can be equal to 4 or 8 to 12. So for all these values of N, the boron halogen compounds or boron halogen compounds of this formula BnXN with closure structure, closure polyhedral structure, are already reported. And when X is equal to Br, then N can be equal to 7 to 10. So three different types of this boron halogen compounds of this formula, when Br is there, is known, while when X is equal to I, N is equal to 9. So that is, we have a compound B9I9 with closure polyhedral structure is now reported. So these are different types of binary boron halogen compounds. Apart from these, there are again numerous non-stoichiometric boron halogen compounds have been already reported, but the chemistry of these compounds are not very well defined, and the structures are also not very have not been established so far. So we'll refrain from discussing the chemistry of these non-stoichiometric boron halogen compounds here, and we'll stick to these stoichiometric binary boron halogen compounds here. So let us first discuss the chemistry of these boron trihalides. These boron trihalides are volatile as well as they are highly reactive compounds, and the BF3 as well as BCl3 at the room temperature, these two compounds exist as gas, while BBr3 is a liquid at room temperature and Bi3 is a solid. So the physical features of these compounds vary depending upon which halogen is present. And then also, if we look at the structure of these compounds, what we will find is that all of these four compounds have same structure, that is the trigonal planar structure for all of these compounds. And so the halogen atoms are attached to the boron center in this fashion. So all of these atoms lie on the plane of this, on the same plane, that is on the plane of this board. Now, if we look at the hybridization of the boron centers in these boron trihalides, we see that the boron center is sp2 hybridized. So each of these three sp2 hybridized lobes on the boron centers essentially bind to a p orbital on the halogen to form three sigma bonds in this fashion, and that is the reason why the bond angle here, or XBX bond angle, in case of all these boron trihalides, are exactly equal to 120 degree, which tells us that the hybridization on the boron atom must be sp2 hybridization. Now, because boron, if we look at the electronic configuration of boron, once again here, that is 2s and 2p, we know this is the electronic configuration of boron, and when boron undergoes sp2 hybridization, then we will have this sort of, these are the three sp2 hybridized orbitals, and we will have one electron each on these sp2 hybridized orbitals, while this unhybridized p orbital in the boron's center is going to remain empty. Now these sp2 hybridized orbitals form sigma bond with the unpaired electron that is present in the p orbital of the halogens, and that is how it forms three sigma bonds with the three halogen atoms, while this p orbital remains empty. And this p orbital on the boron center is actually perpendicular to the plane of this Bx bond plane, the plane containing the Bx boron and the boron atom and the halogen atoms here. And now this p orbital can participate in p pi bonding with the field orbital of the halogens, because the halogens, we know the electronic configuration of the halogens is say for fluorine, if we write, then it is 2s and 2p These are all filled, while one of the p orbital is singly occupied, and this p orbital, that is singly occupied p orbital, is essentially used for formation of this sigma bond here with the boron atom, and the rest of these electrons are present as lone pair of electrons. On these two are present on the p orbital, while this one is present on a s orbital. Now these p orbitals on the halogen atoms in the boron center can now, because they are filled p orbitals here, so these p orbitals are going to donate electron density to the empty p orbital on the boron center, and this is how we can have formation of p pi pi bonding in case of BX3, in case of all the boron halogen compounds, boron trihalides. So let us try to draw this picture in a better way here, because let us put these on a plane, which is, let's put the halogen atoms on plane perpendicular to the plane of the board. So now we can draw the p orbitals in this fashion. So these are all filled p orbitals here, and the p orbital on the boron center is empty. So we can have this sort of interaction. Is we can draw the p pi interaction in this fashion. So this is how the boron center in boron trihalides accept electron density from the halogen atoms. Now the extent of this pi bonding is different in case of different halogens, or in case of different boron trihalide, because in case of fluorine, the orbitals or the empty the p orbital which carries these lone pair of electrons which interact, which form this p pi interaction with the boron 2p orbital. This is a 2p orbital in case of fluorine, while in case of chlorine, the orbital which contain this lone pair of electron is going to be a 3p orbital, while for bromine it is going to be a 4p orbital, and for iodine it is going to be a 5p orbital. Since this p orbital interacts with 2p orbital or empty 2p orbital of boron, so that is why when we change the orbital from 2p to 3p to 4p or 5p, when we change the halogens, so the extent of it, because of the difference in energy between the p orbital of the boron center and the p orbital of the halogen, when we have say iodine, we have a 5p orbital, so there is large difference in energy between the p orbital on iodine and the p orbital on boron, and that is why the p pi interaction or the electron donation to the empty p orbital on the boron center is not very effective, and the p pi interaction or the extent of p pi interaction in case of Bi3 is going to be lowest, while in case of BF3 this p pi interaction is going to be largest, because the p orbitals have similar energy for the fluorine and the boron as center in case of BF3. So this is why the extent of, or this is how the extent of p pi interaction varies in case of different trihalides, and this essentially also translates into the Lewis acidity of these boron trihalides, because we know that these boron trihalides, the boron atom is essentially electron deficient because of the presence of this empty p orbital in the boron center, and that is why these boron trihalides can form again Lewis acid base adapt with different Lewis bases. The way boron hydrogen compounds or B2H6, we have seen that it forms Lewis acid base adapt with different Lewis base. Similarly, boron trihalides can also form Lewis acid base adducts, and the tendency to form Lewis acid base adduct or the Lewis acidity is going to be highest for Bi3, because here uh, when the Lewis base, the incoming Lewis base comes and attack on the boron center here, the boron the geometry of the boron center here has to change from trigonal planar to tetrahedral, because and for this p pi interaction has to be disrupted. In that case, when the geometry changes from trigonal planar to tetrahedral, this p pi interaction has to get disrupted. And since the p pi interaction in Bi3 is lowest, and that is why this attack of this Lewis base is highly facilitated in case of Bi3, while in case of Bf3, this p pi interaction is strong, and that is why there is a resistance to change the geometry from trigonal planar to tetrahedral, and the Lewis acidity of Bf3 is lowest among all of these boron trihalides. So that is why when we write the order of Lewis, increasing order of Lewis acidity of these boron trihalides, we have to write it in this way. Though if one look at the electronegativity of the halogens and then try to decide the Lewis acidity of the boron trihalides, and one would expect that Bf3 has the highest Lewis acidity and Bi3 has lowest Lewis acidity, but that is not the case. The order is exactly reverse of that, and that the reason for this difference in Lewis acidity is because of the p pi interaction between the halogen and the boron center in case of these boron trihalides. Now, we may already know that Bf3 is used as a catalyst in organic chemistry. It is used as a Lewis acid catalyst in Friedel-Crafts reaction, alkylation as well as acylation reaction, and you may have already studied about it in organic chemistry. So the synthesis or the production of Bf3 has industrial importance because it is used as Lewis acid is an important organic reaction, and the industrial method for preparation of Bf3 is one starts with fluorspar, that is calcium fluoride, and then react it with metal borates, that is Na2B4O7 or boron oxide as well, in acidic medium. So this gives you essentially NaHSO4 as well as calcium sulfate, H2O, and Bf3 as well. So we'll have, if we try to balance this equation, we have to write 4Bf3 because B4 is present here, and then that is 12. So this is going to be 6 here, and this has to be equal to 2, and this is also going to be equal to 6, and that is why we have to write this to be equal to 8 here. So 16, so 2, and then 7 H2O is going to be there. So this is how Bf3 is prepared industrially by this reaction of this fluorspar with sodium borate here in acidic medium. So Bf3 is prepared industrially by using this particular reaction. And then in the laboratory, of course, one can use a different method. That is, one can start with phenyl diazonium tetrafluoroborate, and then upon thermal decomposition of this compound, one can obtain Bf3 in the laboratory. So this is the laboratory method of preparation of BF3 because it is an important Lewis acid used as a catalyst in Fieldcraft alkylation or acylation reactions. So we already discussed about other types of boron halides. That is, we have discussed that we have B2X4. This type of boron halides are also well known, and if you look at the structure of these B2X4 molecules, that is for B2F4, say the structure of B2F4 is like the structure of N2O4. N2O4 because these two are isoelectronic species and the structure is also similar for N2O4 as well as for B2F4, and in this case all the fluorine atoms and as well as the boron atoms lie on the same plane, so we can assume that the fluorine atoms as well as the boron atoms lie on the plane of the board here, and that is the structure of B2Cl4 is also similar to the structure of B2F4, and it also in this case as well all the atoms lie on the same plane, that is the plane of this board. But the structure of B2 BBR4 as well as B2I4 are different from the structure of B2F4 or B2Cl4 simply because the both bromine centers here they are quite bulkier as compared to the chlorine or fluorine atoms here, and that is why we cannot place the atoms on the same plane here, and instead we can write two of the bromine center on the plane of the board while the other two bromine centers are going to be on a plane which is perpendicular to the plane of this board. So this is how we can write or we can draw the structure of B2 BBR4 and the structure of B2I4, which is not yet determined, but the structure is assumed to be similar to the structure of B2 BBR4. So then we have already discussed about the about another class of boron halogen compounds, that is BN XN, and we say that the structure of these sort of compounds they are like they have closo polyhedral structure, and we already know how to draw the structure of these polyhedrons starting from n equal to 4 tetrahedron to dodecahedron. We have drawn this, or to we have drawn these structures, as well as for icosahedron also we have drawn this structure. So we can draw the structure of these boron halogen compounds in the same way. Say for example B4 Cl4, if we want to draw this structure, then we know that the structure is going to be tetrahedral, so we can write and the Cl atoms, there these Cl terminal bonds are present. The way it is there, BH terminal bonds are present in case of closo borans. Here also the structure is closed polyhedral structure like the ones in case of closo borans. So this essentially brings us to the end of this lecture. What we have learned or what we have discussed during this lecture is about the boron halogen compounds, and we have seen different types of binary boron halogen compounds that are known. So we have seen the boron trihalides are known, as well as B2X4 type of compounds are also known, and then we have seen that some higher cation-related compounds for boron halogen compounds for fluorine, a boron fluorine compound are known. Say for example, B3F5 as well as B8F12. These two examples we have seen. And then apart from that, another class of boron halogen compound which has closer polyhedral structure, and the empirical formula for this type of compound is BNXN type of compound. And then after that, we discussed about the chemistry of boron trihalides in more detail, and we have discussed about the structure of these boron trihalides. We have seen that the structure of these compounds are essentially trigonal planar, and we have also seen how the Lewis acidity of these boron trihalide change, and because of the p pi interaction between the empty p orbital on the boron atom and the filled p orbital on the halogen center, and that Bi3 or the Lewis acidity of Bi3 is highest among all of these boron trihalides, while the Lewis acidity of BF3 is lowest. Then we have also discussed the application of BF3 in organic chemistry, and we discussed about the preparation of BF3 in industrial scale as well as in laboratory scale. And finally, we have discussed about the structure of other types of boron halogen compounds. That is, we have discussed about the B2X4 type of compounds as well as BNXN type of compounds. So let me conclude this lecture with this, and I thank you very much for being with me during this lecture.